Hello everyone, welcome back to Statistics. Here's Jonathan, and I'd like to start lecture 10, the central limit theorem. So let's start by explaining the theorem itself. Suppose that you have a sequence of n random variables, size n. The sequence is independent and identically distributed, meaning that they have the same distribution. For example, if x1 has a binomial distribution with n equals to 10 and p equals to 1/2, also x2 has the same distribution and also x3 till xn. That's what we mean by saying identically distributed, and also they are independent. In short, we write IID. And they are drawn from a distribution with the expected value denoted as mu and variance denoted as sigma squared. The theorem says that in case n is large enough, in our case we mean n is at least 30, then the average is approximately normally distributed with mu and sigma squared over n. And the sum of xi, starting from 1 to n, is approximately normally distributed with n mu and n sigma squared. Now, it's very important not to be confused with the theorem that we mentioned on the previous lecture. The previous lecture, we mentioned the theorem that says that if we have a sequence of independent random variable, normally distributed with mu and sigma squared, then the theorem says that the average is normally distributed with mu and sigma squared over n, and also sigma xi from 1 to n is normally distributed with n mu and n sigma squared. So it seems like the same theorem, but it's not the same theorem. Why? Because here we need to check that the sequence is normally distributed. If x1 till xn is not normally distributed, then we can't really use the theorem. The central limit theorem says something else. If the sequence has the same distribution, identically distributed, and independent, and n is large enough, then the average is approximately normally distributed, and the sigma xi also is approximately normally distributed. So here, when we use the central limit theorem, we don't need to show that x1 till xn is normally distributed because it works for any distribution, and that's what makes the central limit so powerful. Okay, because again, it works for any distribution, and in the end, somehow, and that's the magic. Okay, we won't prove that. In the end, we go back to the normal distribution. So we start by some distribution, can be binomial distribution, can be geometric distribution, can be any distribution, and in the end, if n is large enough, the average is approximately normally distributed and sigma xi is approximately normally distributed. So again, that's what makes the central limit theorem so important and so powerful, okay? Because we start by distribution, and in the end, we can say something about the average and the sum, and not just that, we know also that it's approximately normally distributed. So let's have an example on the next slide. So here's the example. Suppose that we have a building with 30 apartments and a parking lot with 40 parking spaces. The following is the probability function of number of cars per family in the neighborhood where the building is located. So here's the random variable. Here's the distribution, the probability function of x of the number of cars per family. So just to be sure that we understand and we know how to read this probability function, so let me just explain what we see exactly here. So suppose that we choose randomly a family from this specific neighborhood, and we want to compute the probability that he has 0 cars, so that's 0,2, the probability that he has 1 car, that's 0,4, 2 cars, 0,3, and 3 cars, 0,1. Okay, so now we assume that the families are independent relatively to their cars. A, what is the probability that the parking lot will add enough space for all cars in the building? So let me try to explain how do we solve those types of questions. So here's the solution. First, we need to understand that we have 30 apartments. So that's given to us in the question. So that means that we have x1, the number of cars for the first family, for the second family, and so on till x30. Now, if I ask you how many cars do we have in total, you need to understand that you need to sum x1 plus x2 till x30, because each one of them, each of those random variables represent the number of cars of a specific family, the first one, second one, till the last one. Okay, so in the end, that represents the number of cars in total. And we can, of course, denote it as sigma xi, I starts from 1 to 30. Great. Now, the question is, what is the probability that in the end we'll have enough space for all cars in the building? That means that if we take the total of cars, in order to have enough space, and we know there are in total 40 parking spaces, this number needs to be at most 40. That's what we mean by enough space for all cars. And that's the probability that we want to compute. Now, we are going to use CLT. How? So we are going to use the second part of CLT that says that in case that we have a sequence, let me write it here, in case we have a sequence of n random variables that are identically and independent, then with the expected value mu and variance sigma squared, then the theorem says that the sum of xi I starting from 1 to n is normally distributed, approximately normally distributed with mu and n sigma squared. Okay, so let's try to check those conditions. So first of all, can we say that x1 till xn are independent? So in this case, it's mentioned in the question that they are independent, and therefore that holds. Now we need to compute the expected value of the random variable, the variance of the random variable. So let's do it here. How exactly we compute the expected value of x, denoted as mu? We take each value. We already said that before. Okay, we talked already about the expected values. We take each value multiplied by the probability, and so on. And if you do that, you'll get 1.3. Now let's compute the variance. So we're going to use the work formula that says that that's the expected value of x squared minus the expected value of x, all of that squared. How we compute the variance? So we already talked about it. We take each value squared it and multiply by the probability. So 0 squared times 0,2 plus 1 squared times 0,4 plus 2 squared times 0,3 plus 3 squared times 0,1. And in the end, we need to subtract the expected value squared. And if you do that, you'll get 0.81. Okay, let's continue the next slide. Okay, so now that we computed mu and the variance, the expected value and the variance, now we can use the CLT. So first of all, please notice that, again, they are identically distributed and independent. And also, we need to check that n is large enough, meaning that n is at least 30. In this case, we have 30 apartments, and therefore, that's okay. We can continue with the conclusion of the CLT. Okay, so according to the conclusion, so from CLT, we know that sum of xi from 1 to n is normally distributed, approximately normally distributed with n times mu. So n, that's the number of compartments, so 30 times mu 1.3, and n times sigma squared, 30 times 0.81. And that equals to n with what the parameters are here. So it's going to be 39 and 4.93 squared. Okay, and let's go back to the question itself. So we need to compute the probability that sigma xi is less than or equal to 40. We can normalize it. So we take the value, subtract the expected value, and divide by the standard deviation. So that's the variance. Therefore, if you take the square root, the standard deviation would be 4.93. So that equals to the probability that z is less than or equals to 0.2. And using the z table, we'll get 0.5793. So that's the probability that we'll have a knife space in the building. Okay, so now B, how many parking spaces need to be such that the probability of all cars will have a parking space is 90%? Okay, so now we are asking a different question compared to A. Now we want the value such that the probability that sigma xi is I starting from 1 to 30. So we want to find this value, G, such that the probability is 0.9. Okay, on the previous question, G was given to you. Okay, and we needed to compute the probability. And now we need to find the parking spaces such that the probability of all cars will have a parking space is 90%. Okay, now how exactly we solve those types of questions? We need just to normalize. Again, use the CLT, so we already used it, so we can just use the same as we did before. How we normalize, we take G, subtract the expected value, and divide by the standard deviation. That equals to 0.9. Next, we need to use the Z table and check what is the value here, such that in the end we'll get 0.9. The value, if you remember, and if not, so you can use the Z table, it's 1.282. That means that G minus 39 over 4.93 equals to 1.282, meaning that G equals to 45.32, so it means that it's approximately 46. That means that if you have 46 parking spaces, the probability that all cars will have a parking space is 90%. Okay, let's continue with another example. Suppose that we have a sequence of 50 random variables that are IID, independent and identically distributed, with the following probability function. So that means that each one of those random variables has the same probability function, and also they are independent. We want to compute the probability that the average is at most 6.5. Okay, so how do we solve this question? First, we are going to check if the conditions of CLT, the central limit theorem, holds. So again, according to CLT, we need to check if it's a sequence that is identically and independent, so in this case, at odds. We need also to check that n is large enough. Here, n equals to 50. Of course, 50 is bigger than 30, and therefore at odds. Now, because we want to compute the probability of the average, we're going to use the conclusion that says that the average is approximately normally distributed with mu and sigma squared over n, where mu is the expected value of the probability function, and sigma squared, that's the variance of the probability function. Okay, now let's compute the expected value. So the mu, the expected value of x, we need to take each value times the probability, and so on. So in the end, if you do that, you'll get that the expected value equals to 5.9. Next, let's compute the variance of x. So we need to take each value, square it, and multiply by the probability. And so on. 10 squared times 0.4. And again, we need to subtract the expected value squared. So 5.9 squared. So if you do that, you'll get 13.49. Okay, now we want to compute the probability that the average is at most 6.5. So by using the CLT, we can normalize it. Meaning we take the value itself, subtract the expected value. So let me write here, the expected value is 5.9, and the variance of the average, that's 30.49 divided by the sample size, so in this case, 50. So here we go to the question, the probability that the average is at most 6.5, we're going to normalize, we take the value, subtract the expected value, and then divide by the standard deviation of the average. So that's the variance. How do we get the standard deviation? We need to take the square root. So the square root of 13.49 over 50. So if you use your calculator, you'll get that that's 1.16, and that's exactly by using the z-table 0.877. So that's the probability that the average is at most 6.5. And that ends lecture number 10.